Welcome back to this week of this course. So far during last week, we have discussed in depth about the glucose sensor. So, based on the basic reaction where glucose is converted into gluconolactone and oxygen which is taking part in this reaction in the presence of enzyme glucose oxidase gets reduced to hydrogen peroxide, and then eventually hydrogen peroxide is being oxidized back, and the amount of electron which are being generated during that process is evaluated, and most of the sensors function with that principle. So far all what we have studied is based on glucose oxidase enzyme, which are called enzymatic glucose sensor. But then if you look at the reaction, is glucose plus oxygen leading to the formation of gluconolactone and hydrogen peroxide. This reaction is basically you are oxidizing the glucose molecule. Now, oxidation is taking place or is being orchestrated by the glucose oxidase enzyme. Now, say for example, you remove that enzyme, could you achieve that reaction? Theoretically speaking, you can achieve that reaction provided you can create an oxidizing environment. And how you can create an oxidizing environment is, you can, when we talk about oxidation, we are talking about removal of electrons, and when we talk about reduction, we mean addition of electrons. So, now using the basics of current electricity, you can create a situation where there will be excess of electron and thereby orchestrating reduction phenomena, and the reverse of it, when you remove the electron from a surface, you create oxidation. This is the basic fundamental principle based on which non-enzymatic glucose sensor development proceeded during last 20 to 30 years. And currently, this is one of the very big front runner in the future glucose determination for diabetic patient and detecting glucose in other body fluids like interstitial fluid, like sweat, tears, and apart from it, for any point of care devices, these kind of sensors are being used, and further for non-invasive detection, non-enzymatic methods are being used. In the last class, we discussed one of the challenges of enzymatic method is that first of all, you need very high quality enzyme. Second, the reactant has to come close to the enzyme. But when you are using a heterogeneous sample like sweat or blood or urine or tears, they contain a lot of other interfering molecules, and these interfering molecules act as a barrier for the glucose molecule to reach to its enzyme. So, if this is your glucose oxidase enzyme, there are a lot of obstruction. So, these are some of the major challenges what led scientists, developers, technologists to look for alternative route to detect glucose, and that is where today's class will proceed, non-enzymatic glucose sensor. So, basically there are multiple ways how non-enzymatic glucose sensors are being used, but before we get into that, So, glucose oxidase based biosensors have been studied extensively as we discussed earlier. However, the possible decrease in the catalytic activity of the enzyme arising from the immobilization process. So, this is another aspect we discussed in the last class, where he said because of the immobilization process, the enzymatic activity is being compromised. It is something like when we talk about immobilization, we are trapping the enzyme. So, say for example, there is a pocket, you are trapping that enzyme. When you are trapping that enzyme, it is no more in its native state. You can call it a near native state, but it is no more in the native state, because by trapping process, whatsoever it is, if it is a chemical trapping or it is adsorption, you are altering the topology of the enzyme. The very moment you are altering the topology of the enzyme, there will be change in the bond angles, and that invariably at the angstrom level is going to alter the efficiency of the enzyme. How much soever you try, there will be slightly lesser efficient systems when you are entrapping them, but that is the best people could do. That is why we are following such techniques. Okay. So, still there are great range of challenges for the researcher in terms of performance of the sensor as well as the long term stability of the desired biosensors. Now, direct electro-oxidation of glucose, as we said, glucose plus oxygen, either you need the enzyme to do so, or you can do it electrically, electro-oxidation, and this is the basis of non-enzymatic sensor. In the absence of enzyme, may provide a solution to some of the problems of enzymatic system. However, the selectivity of the catalyst developed towards glucose should be investigated in detail if biosensor is to be used in a highly complex matrix. It is noteworthy that most enzyme-free biosensor for glucose detection exhibit sensitivities at the highest end of the scale in comparison to the enzyme-based glucose sensors. So, this is the basis of non-enzymatic glucose sensors. So, in order to understand, so what one has to develop, so one of the major area where non-enzymatic glucose sensors have proceed is use of wide range of nanomaterials. So, these nanomaterials are used, they are being decorated on a surface sometime like a brush border or sometime like a pillars or sometime like arrays. Using multiple techniques, these could be done using different kind of lithographic tools. Mostly they use photolithographic tools, and what they do is these surfaces have chemical features to conduct electro-oxidation or electro-reduction, or with multiple layer, both oxidation and reduction. And there are multiple nanomaterials which are used for this, like zinc, cobalt, and series of others. So, we will see few case studies, like the first we will talk about vertically aligned zinc oxide nanorods, which were grown on fluorine doped F2 electrode. Okay. So, if you look at the picture, it is something like this. So, you have zinc oxide. So, these are the zinc oxides. Now, hydrothermally grown zinc oxide nanorods on the electrode surface were then modified with copper oxide nanostructure. Okay. Now, this is where you have the copper oxide nanostructure. So, first of all, you make these rods of zinc oxide ZNO. On top of that, you have a deposition of copper oxide. Okay. This is what you see, the copper oxide is being deposited, and copper can change its oxidation state from 2 to 3 by either donating an electron or reverse from 3 to 2 by accepting an electron. So, the copper can, this is the reaction of importance where copper 2 becomes copper 3 by donating an electron. Okay. Copper 2 to copper 3 by leaving an electron, donating an electron, and for copper 3 to copper 2 by accepting an electron. So, this process is the reduction process, and here you have the oxidation process which is happening on the surface. So, now what they are doing is that vertically aligned, as you could see, there are vertically aligned zinc structures, zinc rods. On top of that, you have the copper which is being deposited. The hydrothermally grown zinc rods on the electrode surface were then modified with copper oxide nanostructure through a dip coating and annealing process. The resulting hybrid CuO and ZNO material was coated with Nafion to reduce the possible fouling and help to limit possible interference effect. Further, Nafion also help in mobility of the ions, as well as it makes it more conductive. Okay. The resulting hybrid sensor exhibit a sensitivity of 2961.7 microampere with excellent reproducibility and repeatability, stability and selectivity. So, if you remember these words, reproducible, repeatability, stability and selectivity. Furthermore, the sensor was also used to determine glucose concentration in real human serum sample. The high performance of the sensor was attributed to the efficient electrocatalyst behavior of copper oxide and zinc oxide hybrid material for glucose oxidation. So, this is one of the very promising material which is currently being explored by several groups in the world as well as in the industry. So, what you see in picture A is the schematic illustration of non-enzymatic glucose sensor fabrication and its application. Now, if we go to the next one, which is the B, recently a flexible non-enzymatic glucose biosensor based on laser induced graphene electrode modified with copper nanoparticle has been reported. So, here what they have done, they have the graphene base, again it is the copper on top. So, you have the graphene base on top, there are copper. So, the reason to use graphene is, as all of you are aware of the fact that graphene is a single or a monolayer of with extraordinary electrical properties and optical properties. On top of that, you are decorating it with copper. Okay. The flexible graphene electrode were prepared by laser irradiation of the surface of a sample of polyimide shown in figure B. Since high intensity laser radiation is applied, the polyimide is essentially depolymerized, which leads to the subsequent carbonization and eventually graphitization. The resulting three-dimensional porous laser-induced graphene LIG, which is the short form of laser-induced graphene electrode obtained, were modified with copper nanoparticle. The as prepared. So, first we talk about ZNO CO. Now, we are talking about copper nanoparticle and LIG laser induced graphene. This is the second advancement, demonstrated a glucose sensitivity of 495 microampere. Authors refer to the use of such simple method for fabrication of sensor devices, suggest that their approach could be attractive in terms of fabrication of next generation flexible diagnostic devices. So, now we are entering into the area of flexi bioelectronics or biosensors. This is an emerging area across the world, although the need for high intensity laser irradiation rather calls this presumption into question, because whenever we are using high end technologies, obviously the manufacturing cost is increasing. So, there is a compromise. So, here is the whole process, what is happening. So, you could see. So, you are doing the laser irradiation, you are creating the surface, and then you are doping the surface with copper, and then here is the reaction is happening there. So, this is the schematic of the copper nanoparticle and laser induced graphene sensors. Now, next we move to the third sensor, which is a novel hybrid non-enzymatic glucose sensors consist of freestanding copper hydroxide. So, we started with CuOZNO, then we move to copper NPs and graphene oxide, laser induced graphene. Now, we are moving into freestanding copper hydroxide nanograss. As I mentioned, if you remember, there are different ways you can do it. One of the ways is decorated on surface like a brush border, pillars, arrays, dots, grass. These are different terminologies which are being used. It is essentially how you are arranging the nanomaterial or decorating the surface of the electrode or the electrocatalyst in a certain pattern, in a certain array, in order to maximize the surface contact. This whole array business, when we are talking about these kind of surfaces, what you are essentially doing? You are basically increasing the amount of surface area for the reactant to react, because underneath you have the electrodes. So, the more the surface area, more are your detectable success. Lesser the surface area, lesser will be the detectability of your surface. So, the efficiency is a direct correlation with the amount of contact between the reactant and the surface where the whole reaction will happen. Could be enzyme surface. In this case, it is a non-enzymatic electrocatalyst surface of copper oxide, zinc oxide hybrid, or copper oxide laser induced graphene substrate, or the third one what we are talking about now is copper hydroxide standing surface or standalone surface. So, what is being done here is that in figure C, these authors first prepared a nanoporous copper substrate from copper, zirconium, aluminum glassy precursor via chemical dealloying process. Then the copper hydroxide nanograss was synthesized on NPC substrate through an oxidative alkaline method, wherein the morphology of the nanograss was tailored and varying etching time. The substrate was placed into solution into H4, S2O8 and NaOH until the surface color turned light blue. This process was explained in terms of 4 stages: oxidation, self-assembly, germination and growth. The resulting uniform hybrid also grew homogeneously. It was found that the nanograss cluster exhibited high performance towards oxidation of glucose with sensitivity of 2.09 milliampere has been recorded till this date. And if you look at the whole process, this is the whole process what we are talking about. So, you have the first set of reactions happening here, NPC substrate, then here you have the copper hydroxide nanocrystal formation, and there is a self assembly leading to what they call is as the nanograss, and then these nanograss is kind of some of them pops out and they call it the germination. Here is the growth phase, and this is the final substrate on which the reaction is happening. So, this is these are the kind of advancement which is happening. Next, of course, in the next class we will go for the fourth one. So, this gives you an idea the kind of things what are happening by interfacing nanomaterials, nanoengineering in the area of biosensors. So, we started with enzymatic assays, and now we are talking more and more about non-enzymatic routes of detection. So, I will close the class here. We will move to another such example, and then we will have a summary sheet of the different detection tools what we have done before we move to some in-depth detail of the electrochemical sensors. Thank you.